Section 3.11 again, relative rates. Today, I want to show you more examples about this topic. Take a review. A. In this section, a rate is a derivative with respect to the time t. For example, when you take derivative on the position of a moving object, then you will have the rate of change about the position of the object. That is, you will have the velocity of the object. B. I suggest the following 4 steps when you solve the problems in this section. Step 1. Draw a diagram about the problem that you are solving. Step 2. Introduce variables. Step 3. Determine what are given and what we need to find. Step 4. Find a relation between the unknown and the givens. Example 1. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic cm per second. How fast is the radius of the balloon increasing at the instant when the diameter is 50 cm? To answer the question, step 1, draw a diagram. Here is the balloon. Step 2, introduce variables. I let V below the volume of the balloon and R the radius of the balloon. Please note that radius and volume both are changing. They depend on the time t. Therefore, they are functions of the time t. Step 3. Determine what are given and what we need to find. Initially, when time is 0, the volume of the balloon may or may not be 0. I don't know. But as the volume increases, I'm sure there must be some instant when the diameter is 50 cm or the radius is 25 cm. Let me denote that instant by t0. That is, when time is t0, the radius is 25. Moreover, the volume of the balloon increases at a rate of 100 cubic cm per second. That is, the derivative of the volume is 100. These are all given to us. About what we need to find. We need to find the rate of the change of the radius at the instant when the diameter is 50 cm. Namely, we need to compute the derivative of the radius. Derivative of the radius is the instantaneous rate of change of the radius at a general time t. After the derivative is computed, evaluate the derivative at the time t0 to get the rate of change of the radius at the instant when the diameter is 50 cm. Step 4. Relate the unknown to the given. A relation between the volume and the radius is from the volume formula of a sphere. the volume is 4/3 times pi times r to the third. Now, take derivative with respect to the time t on the both sides of this equation. Then I have this equation. Move out the constant, then I have this equation. Apply the chain rule to this derivative, then I have this equation. The derivative of r to the third with respect to r by the formula for power functions, it is 3 times r squared. Now, simplify the right side a little bit by canceling the number 3. Then I have this equation. Now, solve this equation for dr dt by moving 4 pi r squared to the left side. Then I have this equation. This is the derivative of r with respect to the time t. Now, consider the instant when time is t0. When time is t0, the radius is 25, and the rate of change of the volume is 100. Plug in this information in this equation. Then, derivative of r at t0 is 100 over 4 pi times 25 squared. It is 1/25 pi. The units is cm per second. Conclusion. The radius of the balloon is increasing at the rate of 1/25 pi cm per second at the instant when the diameter is 50 cm. Example 2. A water tank has the shape of an inverted circular cone with base, radius 2 meters, and height 4 meters. If water is being pumped into the tank at a rate of 2 cubic meters per minute, find the rate at which the water level is rising at the instant when the water is 3 meters deep. To solve the problem, step 1, draw a diagram. Here is the water tank. The shape of the tank is an inverted circular cone. The base of the cone is a circle with radius 2 meters. The height of the cone is 4 meters. Water is entering the tank at a rate of 2 cubic meters per minute. Step 2, introduce variables. Let V denote the volume of the water in the tank. R, the radius of the water surface. And H, the height of the water. Volume, radius, and height, they are not constants because water is entering the tank. They are functions of time. Step 3, determine what are given and what to find. Water is entering the tank at a rate of 2 cubic meters per minute. 2 cubic meters per minute is the rate of change of variable V. V is the volume of the water in the tank. That is derivative of V is equal to 2. Moreover, the water level is rising because water is entering the tank. There must be an instant at which the water level is 3 meters high. Let me denote that instant by T0. In other words, when time is T0, h, the height of the water is 3 meters. These are all the information that we have. We need to determine the rate at which the water level is rising at the instant when the water is 3 meters deep. That is, we need to compute the derivative of h. After we get the derivative of h, evaluate the derivative at T0. T0 is the instant when the water is 3 meters deep. Step 4. Relate the unknown to the givens. The unknown is dh dt and the given is dv dt. We want to find a relation between them. A relation among v, r, and h is given by this equation. This equation is the volume formula of a circular cone. But this equation is a relation about v, r, and h. We want a relation only between v and h. So we want to eliminate r from this equation. In order to eliminate r, we use similar triangles. From the diagram, we can see that the triangle ABC and the triangle ADE, they are similar. So R over H is equal to 2 over 4. We have this equation. From this equation, we then have R is H over 2. Plug in H over 2 in the R here, then R is gone from this equation. Then we have a relation only between V and H. The relation is V is equal to pi over 12 times H to the third. Now, take derivative with respect to the time t, then we have this equation. Move out the constant, then we have this equation. To compare the derivative of h to the third with respect to the time t, we need the chain rule. Write this derivative into this derivative times this derivative. Derivative of h to the third with respect to h is 3h squared. Simplify the right side, then we have this equation. Now, we want dh dt, so move pi h squared over 4 to the left side. Then we have this equation. This is the derivative of h with respect to the time t. Next, evaluate the derivative at the time t0. At t0, h is 3. Derivative of v is 2. Plug in the information in this equation. then the derivative at the time t0 is this number. Now, conclusion. The water level is rising at a rate of this number. This number is 0.28, and the units is meters per minute. The water level is rising at a rate of 0.28 meters per minute at the instant when the water is 3 meters deep. Example 3. A man walks along a straight path at a speed of 4 feet per second. A search light is located on the ground 20 feet from the path and is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? Here is a diagram about this example. This is the man who is walking along this straight path. His walking speed is 4 feet per second. The searchlight is here. The distance between the light and the path is 20. This is the light beam. Focus on the man. Now, let me name this point by B. This point is the point on the path that is the closest to the searchlight. The distance between point B and the man are below it by x. And the angle between the light beam and this line is perpendicular to the path. The angle between the light beam and this line are below it by theta. Because the searchlight is rotating. Theta and x both are changing. They depend on the time t. They are functions of the time t. Initially, when time is 0, the man may be far from point B. Because the man is walking towards the point B, there must be some instant at which the man is 15 feet from point B. Let me denote the instant by t0. That is when time is t0, x is the distance between the man and point B. X is 15. Moreover, the walking speed of the man is 4 feet per second. This is the rate of change of the distance between the man and point B. That is the rate of change of variable x. So, derivative of x is 4 feet per second. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? The point on the path closest to the searchlight is the point B. To answer this question, we need to compute the derivative of the angle theta. The derivative is the rate of change of theta. We consider derivative of theta as the rotating rate of the search line. After we get the derivative, evaluate the derivative at the time t0. Then we have the rotating rate of the search line at the instant when the man is 15 feet from point B. The unknown is derivative of data, and the given is derivative of x. We want a relation between them. A relation between x and data is from this right triangle. Tangent of data is the opposite sine x over the adjacent sine 20. We have this equation. Now move 20 to the right side, then we have this equation. Take derivative with respect to the time t on this equation. Then we have this equation. Apply the chain rule to this derivative by inserting d data to the bottom and to the top. We have this equation. Derivative of tangent of data with respect to data by formula is secant squared data. Recall that secant is 1 over cosine. So secant squared is 1 over cosine squared. So we have this equation. Now move 20 and cosine squared to the left side, then derivative of data is this. Now consider the time t0. When time is t0, x is 15. Apply the pi diagram theorem to this triangle. Then we have AC. AC is the hypotenuse of the triangle. AC is equal to square root of AB squared plus BC squared. AB, this edge is 20. So here 20 squared. BC, BC is x. X depends on the time t. But when t is t0, x is 15. So 15 squared. Therefore, when the time is t0, AC is 25. Recall that cosine of data is equal to adjacent sine over hypotenuse. So cosine of data is AB over AC. AB 20. AC at t0, AC is 25. Therefore, at t0, cosine of data is 4 over 5. Plug in 4 over 5 in the cosine of data here, and plug in 4 in dx dt here. Then derivative of data at the time t0 is this number. This number is 0.128. Conclusion. The search line is rotating at a rate of 0.128 radian per second when the man is 15 feet from the point on the path closest to the search line.